So here's the theorem again, stated: if an L theory T is consistent, it has a model. So how does the process work? So we start with T, and first we extend it to Hankin theory, right? So TH, that's our Hankin extension. And then we complete it. So denote this by TH star. Right? To make the whole following slides a little bit more readable, let's denote this complete Hankin extension by T prime. So keep in mind, T prime is a theory over the extended Hankin language LH. So where we added all the Hankin constant that we needed to introduce the Hankin sentences. One important thing to point out here is the following. So in the completion step, we do not extend the language anymore. So we're going from here to here. And since we've already added Hankin sentences for all LH formulas, that is more precisely all LH formula of the form exists x psi, right? We have already added all of those. That means, and we do not extend the language anymore, that means this completion here will also be a Hankin theory. So, in other words, T prime is a complete Hankin theory. And remember that being complete means, in particular, that T prime is consistent. So now we have a consistent, complete Hankin theory that extends T. Now we return to our term models and try to prove the theorem that when we started out with term models and term structures, we were not able to fully push through the whole induction. So again, the claim is for the term structure, so the canonical term structure A prime of our Hankin theory T prime, here, we have that for all LH sentences sigma, A prime satisfies sigma if and only if T prime proves sigma. And of course, proof here is to be thought within the LH language. As before, we try to prove this by induction on the height of sigma, and we hope that now that we have a complete Hankin extension, we're indeed equipped to push this induction all the way through. We already handled the atomic cases. We saw that these are true for any canonical term structure, for any consistent theory. So that's already done. So we only have to focus on the induction cases. So let's start with the first case, where sigma is of the form not psi. So there it holds that not psi is true in A prime, if and only if A does not satisfy psi. That's just the definition of the satisfaction relation. Or in general, for any structure in any sentence. Okay. So, but now by inductive hypothesis, we have passed to a formula of shorter height, right, namely psi. So by inductive hypothesis, we can now see that this is equivalent actually to T prime not proving psi. And now comes the step that we have not been able to do for general T, because T might not be complete. But now that we know that T is complete, right, we can now argue that this is the case if and only if T prime proves not psi. Okay. So we have done this first case. Now let's move on to the second case, where sigma is a conjunction of phi and psi. Again, we start out with the first equivalence here, right, is simply due to the definition of the satisfaction relation, right, namely that A prime satisfies phi and psi if and only if A prime satisfies phi and it also satisfies psi. Now we've reduced the height of the formulas involved here. So we can apply the inductive hypothesis, right? Here, we can make this step here using the inductive hypothesis and pass to, or have the equivalence that this T prime proves phi and T prime proves psi. Again, keep in mind all proofs here are over the extended language LH. And then it's not hard to see, and we did part of that already in class as an exercise, right, that this is equivalent to T prime proving phi and psi. So that completes this case. So far, we haven't really used the Hankin property, but of course this comes into play in the final case where sigma is of the form exists x psi. So let's start as usual. The formula exists x psi holds in A prime if and only if, by definition of the satisfaction relation, right? So here, by definition of the satisfaction relation, if and only if there exists an element of the universe A prime such that if I plug that element into psi and evaluate that inside A prime, this formula holds in A prime. Of course, here we are in a special case where our universe is made up of those equivalence classes of constant terms, right? So here, remember, those were the constant terms. So terms without variable symbols. So that's why in this case, right, what we have here, so what we plug in here is the equivalence class of a term. So this is why we get this equivalence here. There exists a term t in this from the set of constant terms such that if we plug its equivalence class, right, under the t equivalence, t prime equivalence in this case, into psi, we get something that holds in A prime. But now this here is equivalent to just taking the term t, right, and substituting this term t for x. This gives us a sentence, right, because t is a constant term, right, so it eliminates the free variable x, right, becomes a sentence, and this sentence we then can evaluate inside A prime. And by the definition of our term structure, evaluating this sentence, psi with t substituted for x, is the same as checking whether this formula with the assignment equivalence class of t under the term equivalence holds in A prime. Okay. Now, again, we are in a situation where the height is reduced. So now we can use the inductive hypothesis, right, to obtain the equivalence that this holds if and only if there exists a constant term such that t prime proves this sentence, right, where t is substituted for x. Okay. And now the final equivalence we're going to apply, right, is the following here. And this one now really uses that we have a Hankin theory. So that t prime is a Hankin theory. One direction holds generally for theories, right, because we have the axiom that if we have this, we can, this implies this. So from here to here, we can do this generally in theories, but in order to get from here, right, to here, we need that t prime is a Hankin theory. Okay, so, and if we look at this, we have obtained our desired equivalence. And with this case, we now conclude the proof, and we have particularly shown that our canonical term structure is indeed a model of t prime. We're not quite done yet because we need not a model of T prime, but we need a model of T. But to get that, we simply take the reduct, right? So we restrict the canonical term structure A prime simply to all the symbols that were in the original language of L, right? And that will give us a model of T. Keep in mind here that T is a subset of T prime, so since A prime satisfies all formulas of T prime, this reduct, right, which is a structure of the original language L of T, right, will satisfy every sentence in T. And this concludes the proof. We have therefore shown that T has a model. Since we kept track in the countable case of the cardinality of our constructions, so when we, for example, constructed a maximal consistent extension, or we constructed a Hankin extension, we get as a byproduct of this proof of the completeness theorem something that's called Löwenheim's theorem. In particular, note that if our original language L is countable, then so is the extension language LH. Moreover, note that there are only countably many LH terms. Right? And then in particular, this means the canonical term model for TH is countable, right? Because it's made up of equivalence classes of the constant terms, right, of which there are only countably many. So that means the canonical term model is countable, and it follows that if T is a consistent theory in a countable language, then T has a countable model. We finish with one of the most important applications of the completeness theorem, which is known as the compactness theorem. The way we state it here is as follows. If every finite subtheory T0 of T has a model, then T has a model. And the proof is now pretty straightforward and short using the completeness theorem. Namely, right, if every finite T0 in T has a model, that means in particular every finite T0 inside T is consistent. But we know that a theory is consistent if and only if every finite subtheory is consistent, right? Because if inconsistency shows up, it must already show up in a finite subtheory. So that means from this we can conclude that T is consistent. And that now implies that by the model existence theorem, that T has a model. So now apply the model existence theorem or the completeness theorem equivalently.